I have Mr. Ali Khan here. He was our alumni here. So he got his master's degree at WSU, and before that, he got his Bachelor of Engineering from National University of Science and Technology from Islamabad. So, and he is presently working at SEL. So, as an associate engineer at SEL, working on the robust communication system and protocols for leading product line. So it's very important things. Okay, so with that, let's hand it over to Ali and let's listen to his talk. Thank you.
Good morning, everyone. My name is Ali, and I believe you all know me. So let's get straight on to the topic. So can the people on the Teams call hear me? Can anybody confirm if I'm?
Yes. Thank you.
Okay, so the topic we are going to talk about today is policy and regulation in the electric power sector in the United States. We are going to focus specifically on United States because we are studying here now. This policy and regulation can be different in different parts of the world. It's done a little differently in Asian countries, and it's a little bit different in European countries. But today, for this lecture, we are going to focus on the United States. So the first part of our talk is about the organizational and regulatory structure, how the industry is organized, how the regulators are organized, what is state regulation, what is federal regulation. In the next part, we are going to talk about the technical standards. Okay, is it working on here? Slides are not updated here. The screen is not updating.
Oh, let's maybe ask Jenny.
Maybe share?
He's not sharing.
Oh, you're not sharing, right?
Oh, okay. Let me just ask Jenny, so maybe can help. Oh, yeah, you're right. Good.
I thought that.
Okay.
Okay, and just reshare again, and it should work just fine. Is it completely, did it freeze up on you? Let's see.
Now it's working.
Now it is.
Okay.
You have to share.
Yeah, so let's
you sharing?
continue. So yeah, I'm sharing. So in
Okay.
the second part, we are going to talk about the technical
I
standards.
think you're sharing.
So obviously there are standards.
I don't think you're sharing.
Yeah, maybe you share.
Oh, you're sharing through your other.
Yeah.
How about
Okay.
the slides? Does it move forward, backward? Can you go to next slide?
To be able to just do the arrows.
I
Okay,
can
Yeah, we
Okay.
can see it. We can see
Okay,
it.
perfect, great.
Okay. So every industry has its own technical standards, and here in this section, we are going to talk about what are the standards that govern the operation of the electric power sector. You'd be thinking about NERC standards, you'd be thinking about IEEE standards, there are construction standards, and then there are safety standards. So we are going to briefly discuss all of those in this section. And then in the third part of our talk, we are going to talk about the emerging regulatory challenges. And that is going to be the most interesting part of today's talk. So we are going to talk about what challenges the regulators of today are facing. What are they discussing in the public utility commissions? What are the challenges faced by the FERC, and what is basically required to move the wheel of progress in the electric power sector. Following from that, we are going to carry forward into the current energy policy. And in this section, we are going to focus on what the executive branch is propagating as its energy policy in the electric power sector. So as a basic concept, you all should know that an industry follows the policy direction that is defined by the government. So we are going to take a brief look on what is the current energy policy that is being propagated right now in the industry. And then in the last section, I would do it a little bit here. Anyways, let's go with it. So we are going to talk about the effectiveness of the current energy policy. So first we are going to discuss what the energy policy is right now. And then we are going to do a short discussion on how effective that policy is going to be in the coming years. We are going to discuss what are some of the shortcomings, and we are also going to discuss what is the way forward for our industry. Okay, yeah, now it works better. Okay. So a lot of the talk that we are going to talk about today is going to be circulated soon to our ESIC audience in this small booklet that we have written. So the book is titled "The Structure and Current Policy Drivers of the Electricity Sector in the United States," and then Professor Anjan Bose helped me out and supervised me with this project. So it's available free to our ESIC audience, and it's probably going to be out in a week or so. And then I figured out that this is a good opportunity to showcase the cover page. So I got the cover page in place. Okay, so let's move forward with our first part. For ease of categorization, I've divided the organizational structure into 4 parts. Let's see what they are. So the first thing which you would think about is who owns the electric power grid, who owns the transmission lines, who owns the distribution poles, who owns the meters, and who owns the transformers. So it's the utilities that own the distribution infrastructure. We are going to talk about utilities in a little bit more detail in the coming slides. And we discussed earlier how public and private interests are balanced in this industry. So, there are 2 stakeholders. One of them is the industry, and one of them is the consumer. So how the interests of both parties are balanced. It's the regulators and regulation that keep track of those interests and make sure that they do justice between public and the private sector. We're going to look about it in a little bit more detail. So, okay, and then how the grid is operated. What are the organizations? What are the entities involved in the operation of the grid? We're going to talk about under the category of system operation. And then lastly, for the topic on organizational structure, we are going to talk about the technical benchmarks in the heading of standards. So let's go over onto the first category, that is, let's talk about utilities. So utilities here in the United States can be categorized into two broad areas. Some of them, or I would say most of them, are investor-owned utilities. That is about 75% of the customer base. It's not 75% of the area, it's about 75% of the customer base, or the amount or the volume of kilowatt hours being served. And about 25% of the utilities are consumer owned. And we are going to see shortly what's the difference between these 2 categories. So investor owned utilities are private companies. They are owned by investors and they are financed by shareholders' equity. By that, I mean like 5 people gather together and pool capital in a basket, and then they form a utility to provide electricity to an area where they have been mandated to do so by the state regulators. They have a lobbying group that is called Edison Electric Institute. You might have heard of the name before. Let's move on to consumer-owned utilities. They may be, let me take a step back. What's the investor-owned utility in our area?
Avista.
Avista. And then what's the investor-owned utility in Seattle area? Puget Sound Energy, might have heard of the name. So yeah, let's move on to consumer-owned utilities. So they are owned by cities or municipal councils, and they are governed by local city council or an elected commission. Some of the examples are Seattle City Lights, and there are quite a few city-owned utilities around. I think some in Los Angeles, there is a city-owned utility. And then there are public utility districts and cooperatives. There are quite a few in central Washington, Grant County, PUD, you might have heard of the name. So they are governed by elected voters within their service territory, and cooperatives are governed by a board elected by customers of the utility. That's a small difference, but they have their lobbying group as American Public Power Association, and for the cooperatives, this is National Rural Electric Cooperatives Association, or NRECA, you might have heard of the name. In some cases, these three can group together and form G&Ts, that is called generation and transmission cooperatives. So they combine together by way of power sharing contracts. Okay, you have generation, you're gonna provide me generation. I have a transmission line, I can dispatch your generation to a cooperative that is somewhere out there in a different area. So they can combine together to form generation and transmission cooperatives. And then in some areas, they're like Native American lands, there are some other power entities that are independent, mostly in Native American territories. So here you see a map of the major investor-owned utilities in the whole of the continent. So you might be picky on some of the familiar names where our previous alumni have worked, like Duke Energy and National Grid. And another interesting thing you would note about this is there are some white areas. They are not empty areas. They are covered by the second type of utility that we discussed. So this is investor-owned, and other white area is covered by cooperatives and consumer-owned utilities. Okay. Okay, let's move a step forward into the system operation part of our organizational structure. So here I would like to place some emphasis on the NERC's functional model. So according to the NERC functional model, each stakeholder in the organizational structure is given a specific name and assigned a specific function. So for example, there is a reliability coordinator that is responsible for assuring the reliability of the bulk power system. On the right side, you see that there are 1, 2, 3, 4, 5, 6 reliability assurance areas. Why they are different? I mean, there could be one reliability area for the whole continental United States, but they are different because each area has its own generation and transmission requirements. So NERC standards differ a little bit between East and the West. So for this reason, they have formed 6 reliability assurance areas. There is another entity that is probably the most important, that is called a balancing authority. It was previously called control areas, but they updated it to balancing authority. And they are responsible to maintain the load generation interchange in their respective areas and support the interconnection frequency. How they do it and what is the standard with supporting frequency, we're going to talk about it in a little bit of a time. But And then another entity is the ISO and the RTO, Integrated System Operator and Regional Transmission Operator. So they are similar to balancing authorities. In addition to that, they are assigned a function of market operator or transmission operator. So that is responsibility of balancing authority plus the responsibility of running a market operator. ISOs and RTOs are voluntary organizations. They are formed by voluntary clustering of utilities in their area. So let's say there were 5 utilities in this area in the state of New York, and they voluntarily clustered together to form the New York ISO. There were 4 utilities in the California area, and then they voluntarily clustered to form an ISO, that is California Independent System Operator. And okay, we are going to talk about the law that enables them to cluster together to form this market at a slightly later stage. Okay. So moving forward with the system operation, there are 3 synchronous interconnections that you see in this picture here: the Western interconnection, Eastern interconnection, and Texas has a separate interconnection. They are not connected via an AC connection, but they are connected via DC asynchronous connections. And then we talked about 7 ISOs and RTOs. So excluding the Texas Council, there are 7 ISOs that are formed by the voluntarily clustering of utilities. And there are about 66 different balancing authorities. Now, I'm not quoting this number because it keeps on changing. Let's say 2 utilities, 2 balancing authorities decide to combine together and form a single control area. That has happened previously. This number was much higher in the previous years, but it has gradually reduced. And on this map, you can see some of the balancing authority areas. And then there are 6 reliability areas that we showed you in the previous slide. So here, what I want you to take is that these are the terms that are found in the NERC functional model, and it has a certain hierarchy. So the reliability coordinator is on the top, the balancing authority is a little bit down, and RTOs and ISOs, like market operators, lie down there. There are other entities that are present in the NERC functional model, but we have quoted you some of the most important ones. I mean, there are transmission operators, there are load serving entities, there are generation providers. So I think there are about 14 different types of categories here. Okay, so that was system operation. Now let's move forward to regulation. So what is the legal benchmark here? So this not only applies to the electric power sector, it applies to the whole of the legal system here. You live in Idaho, but you do an accident in Washington. Which court you are gonna go to? So since this is an interstate matter, you're gonna go to the federal court. And in this way, this happens in the electric power sector, that anything which comes within the boundaries of the state go to the state regulators. Anything which is beyond the boundaries of the state goes to federal regulators. Let's say interstate transmission, power generated in Washington gets shipped over to power consumed in California. So that interstate transmission is under the regulation of federal law. And we are going to look into what is the entity that governs federal law in this case. So when we talk about regulation, I would divide it into three categories. It may come from the federal government, it may come from the state regulator, and it may come from the local council, like your local county or local city council. So let's see what each of these entities have on their plate, what each of these entities have on their share. So federal regulator, which is the Federal Energy Regulatory Commission, has jurisdiction over whole power sales and interstate transmission. By whole power sale and interstate transmission, I mean operation of the bulk electric power system. That is, you generate power in Washington and transmit it over to California. They have authority over licensing of hydroelectric power facilities, since this is a federal matter. They have authority over offshore wind power, and then reliability standards also fall within the federal jurisdiction. They are made by NERC, North American Electrical Reliability Council, and they are enforced under the authority of w.r.t. So we are gonna look into a little bit more detail onto NERC standards when we talk about our section on standards. Nuclear power also falls within federal jurisdiction, and power marketing authorities also fall within federal jurisdiction. So what is the power marketing authority in our area? Okay, so I can give you two examples. BPA and TVA, Tennessee Valley Authority, they are power marketing authorities. They were formed to administer federal dams, like you have many dams in Washington. So they come under the authority of power marketing authorities. Okay, let's go on to state regulation. So what do state regulators do, and what do they have on their plate? So remember the legal standard. Whatever comes within the boundaries of state goes on to state regulators. They talk with utilities about retail rates and revenue requirements. They wanna see if the rate that is being charged to the customer is fair. They have a fair rate of return. They talk about distribution services and generation portfolios. So state regulators have requirements like the utility must have 10% of power from renewable energy sources, a different percentage from gas, and a different percentage from hydroelectric power. So that is generation portfolios. They have construction standards on their plate. Construction standards refer to, okay, if you want to construct a transmission line through Washington, even if that goes to Idaho or a different state, you go to the state regulator. So the regulator here will evaluate like if that project is really required, or is that project really necessary. So for example, I as a utility propose that I need to build a transmission line and maybe chop through a forest, and so give me the permission to acquire this land. So the regulator is going to decide in this case, which is the state regulator is going to decide if that construction of transmission line is really necessary, or you can go by a different way. So they are responsible for evaluating new construction projects. Quality of service metrics, they will ask the utilities to present their service quality metrics. By that, I mean they're gonna ask you to, okay, so I have 5 minutes of outage per year. I had 100 minutes of outage per year, and I resolved like 500 customer complaints in 3 days. So this is service quality metrics. One interesting part is the regulators also oversee the issuance of stocks and bonds for the utilities. So this is called capital acquisition. So I, as a utility, want to make a new power plant, and then I go to the bank and I take a loan at whatever rate I want, and then start building that power plant. The state regulator is going to make sure that I acquire that capital at a responsible rate, because eventually that cost of that loan is going to be transferred on to the rate payer. So the regulator wants to know that, okay, you take this loan at a reasonable rate. Also, the regulator is going to look into the financial health of the utility. So let's say there was a hurricane in Florida and a lot of transmission and distribution poles got knocked out. Now, the utility wants to raise capital to replace those torn out or blown out infrastructure. So how is it going to do? The state regulator wants to know that you have enough credibility and you have enough financial health that you can go to a bank and get a loan immediately in case of a natural disaster. So now, one interesting distinction here is the state regulation for investor-owned utilities comes from Public Utility Commission. The PUC retains, the PUC governs most of the investor-owned utilities, but not the consumer-owned utilities. So why is that the case? We discussed earlier that consumer-owned utilities are themselves governed by elected councils and by customers of the same utility. So the PUCs think that this form of election is sufficient for doing justice with the customers of the utility. So in most cases, state regulators will regulate investor-owned utilities. And the last part of this is local councils. They would oversee some of the facility sightings, like I want to make a substation here, so I need a land permit. So that goes to the local council. And some environmental impacts, they also overlap with the state and local regulator. So for example, I as a utility make an investment to build a clean power plant. And to build that clean power plant, I spend like $2,000 extra. So the regulator is going to decide if that investment extra, which I made in making my power plant clean, is going to be transferred to the ratepayer or not. Okay. So let's now move on to our section on standards. Standards can be of many types which are applicable throughout the electric power industry. There may be equipment standards, like what should be the voltage rating of this transformer, what should be the IP rating of this inverter. So those come under the category of UL standards, underwriter laboratories. There are reliability standards that are made by NERC. There are management standards made by ISO. And the two more important ones are construction standards and safety standards. Construction standards are made by National Fire Protection Association. One of the most important is the National Electric Code, which tells you about how are you going to lay transmission lines, how are you going to lay underground transmission lines. So it's all about building the electric power infrastructure. Safety standards are made by OSHA, and they would tell you, like, if you are going to work on an energized wire, what PPEs you should wear, how much distance you should be from an energized conductor, and what are the studies, what is the protection you need to put in place to ensure safety of the workers. Environmental standards by EPA and technical standards, you all know that they are made by the IEEE and in some cases the IEC. So for our discussion here, we are gonna focus on the NERC standards. We are not gonna go in a lot of detail, but we are gonna go over briefly so that everybody of you gets a brief flavor of how they look like. So bulk power system is operated according to NERC standards. The important thing about NERC standards is that they apply according to specific time horizons. What are time horizons? So time horizons are, I would describe it by means of a timeline in power system operation. So from minutes into hours, this is called real-time operation, which is also known as automatic generation control. If you go into hours, into like by the end of the day, that is called economic dispatch and also referred to as same-day operations. Beyond days and months into up to 1 year, it's called operations planning. And from 1 year to most utilities take it as 10 years, it's called long-term planning. And I would also add a fifth time horizon that is called contingency. So that is likely a subset of real-time operations. So as we previously discussed, they apply according to time horizons and they apply according to a specific entity. So by entity, I'm referring back to the NERC the entities that are present in the NERC functional model. So they apply according to time horizons and they apply according to a specific entity. They are grouped together into 14 categories. I won't go into the detail of all these categories, but just to quote a few: resource and demand balancing, BAL, critical infrastructure protection, CIP, that is related to cyber security of the grid. And there are 14 categories. So let's look at an example NERC standard. I've quoted here the most important standard. So see how it applies to a specific time horizon and how it applies to a specific entity. So this is the BAL 0012 real power balancing control. There are two key metrics in this standard, the CPS1 and the balancing authority ACE limit. These are used as a benchmark to control the frequency within a balancing authority. There's a detailed process that is mentioned in the standard about how are you going to arrive at these two metrics. But we are not going to go into the detail of that. Another important standard is the disturbance control standard, which is simply put the N-1 criteria. All of you know about that. The standard says that should a contingency event occur, the reserves must be restored to their pre-event state within the reserve restoration period. And then there are reporting standards. So remember the hierarchy in the NERC functional model that we discussed. The reliability assurer is on the top and the balancing authority is liable to report its operational data to the reliability assurer. So this is what they are going to report to the reliability assurer. They must have frequency metering equipment and there is a certain accuracy for that. Their monitoring system must have an uptime greater than 99.5% and they should acquire a data step every 5 seconds. And all of this data must be reported to the reliability assurer in their respective areas. Next, we are going to look at another example from the operations planning perspective in the operations planning time horizon. And this is also built into the hierarchy of the NERC functional model. So transmission operators and balancing authorities. Remember, each standard applies to a specific entity. So this applies to transmission operators and balancing authorities. And the standard says that they are going to make their day ahead operation plans and evaluate their system's operation limits. If any of the limits get exceeded, report to the reliability assurer. So this is where the hierarchy comes. And here is the full list of like standards. This is just to show you about the time horizons and how the standards are linked to the time horizons, but we are not going to go into the detail of it. Okay, so let's move on to the next section of our talk, which is regulatory challenges. So what are the current regulatory challenges that the industry faces today? So if you see here, I'm showing a balance. So the thing here is that let's say there are two sides of the balance. On one side, there is an investor-owned utility, or I would say an investor who has put his money and wants a fair return on investment. On the other side, there is a customer like you and me who want the best service in the least possible money. So who is going to do justice between these two entities? So the job of the regulator is to do justice between these two entities. It has to make sure that whoever made investment in the industry gets a fair share of return, but at the same time, the consumer also pays a fair price for the services it gets. So we are going to look at some of the challenges that are present in making an equitable net metering policy. We are going to look at some of the challenges that are present in the large-scale adoption of EV charging infrastructure. Also, if we have enough time, we are going to look into resource adequacy planning and bulk transmission construction. But if we do not have enough time left, you can always go into the book and the book that I showed in the first slide, and then read about it there.
We have around 10 minutes.
Passed so quickly.
Yeah, time flies.
Okay, so let's just go over two of the regulatory challenges, and then we are going to see how much time we have left. So you might be thinking net metering is an easy job. You just it's a simple administrative process. You would roughly estimate the value of any DER resource, and then you would pay a compensation for that. That was the case when the concept was new in the industry and there were few participants and the number of exported kilowatt hours was small. So the consequences of not doing justice between the stakeholders were also small. But now there are net metering customers all over the network and the exported kilowatt hours has increased. So we see an argument that instead of being beneficial to the industry, it merely transfers the cost of electricity from one segment of the ratepayer to the other segment. So they criticize that those who have net metering are being subsidized by those that actually pay the rate. And this phenomena is called as a cross subsidy. So to understand cross subsidy, you would need to look into how the electricity rate is, what is the composition of the rate? So it includes the cost of generation plants. The utility would buy fuel, build a power plant, includes the cost of transmission systems, you need to build the towers to transport electricity. And then some additional functions, like if you have a power outage, you would give a call to the call center and someone is gonna pick the phone, and that is being paid by the utility. And the last component is the return on investment. So the way this has worked up till now is that this rate is, this cost is factored into the per kilowatt energy price, and then it is levied equally on all consumers. But those that have net metering didn't purchase electricity from the utility. They net zeroed themselves, and this upsets the whole volumetric balance. Consequently, what happens is that the utility is not able to recover its fixed cost. And what it is forced to do is it will shift that burden on the remaining purchasers. This is just like trying to sell fast food in a place where nobody is buying it. So the utility is willing to sell, but the number of customers that purchased it has reduced. So how is the utility going to recover its fixed cost? So they are most likely going to transfer it to those who were previously paying the bills. So those who purchased subsidized those who didn't purchase. And this is the criticism that is coming on towards net metering policies right now. I would like to go into a little bit more detail into the tariff structure, but let's go over that quickly because we are in a paucity of time. So from right to left, you see that previously we had feed-in tariff that was placed in the early years of the industry to subsidize adoption of PV. You would get a fixed rate to recover your capital costs. And then there is the retail rate, that is the current rate being charged to the customer. But now there has been a transition towards the avoided cost rate and the value of the DER rate. If I would explain that quickly, let's say your solar generated 500 megawatt, and then because you got that from solar, the utility did not have to generate that 500 megawatts. So the utility saved on fuel, it saved on transmission cost, it saved on line losses, and it saved on some of its administrative costs. So these are the costs that the utility avoided because of you installing the solar plant. And then there is a more fairer rate that is called value of DER. This one has an extra component on top of the avoided cost rate that is positive externality, which it's a technical term, but they comprise of social benefits like environmental and benefits in terms of reduced carbon footprint. So this is a more rational approach to arrive at a more fairer compensation for a distributed energy resource. Would go into the detail of each of that, but looks like we are a little bit short of time. So the next challenge that the regulators face here is large-scale adoption of EV infrastructure. So as we discussed earlier, like net metering, the sales of EVs are also expected to increase. But the question here is, are there enough chargers to support that increase in the number of electric vehicles? And the regulatory challenge here is that to what extent you should involve the utility in the process of building EV chargers. So I've got this interesting chart or a graphic, you would say, that shows you the different roles a utility can take when it is installing an EV charger. The utility can either be a facilitator. It would treat the request for installation as a new connection request and then sanction a load for it, and will not do anything beyond that. It can be an enabler where it would install the charger itself, the panels and the meters, but will not own them. Or it can be a provider where it would own the EV charger and sell the electricity itself, which you are seeing in the Avista territory in Washington. So the point here is that the more you involve the utility, the more you are going towards a monopolistic market environment. And the less you involve the utility, the more you go towards competition. So if you enable participation of other stakeholders, you are going to add competitors into the industry, and critics argue that competition is going to enhance the industry. So it is going to be lower the price and it is going to give consumers more options. Whereas proponents of utility involvement argue that utilities are experts in delivering power. They know their distribution infrastructure, they know where the load is, and they know what are the safety standards. So proponents argue that it's better to leave EV chargers to the utilities and give them that monopolistic market segment. Now, if you involve the utility in this whole value chain from here to here, obviously there would be a cost that would be spent in building this infrastructure line. So now the question which the regulators face is, should this be recovered from the ratepayer money? Like I own a big diesel truck. I don't need an EV charger. So why should I pay for the EV charger that is being placed in the parking? So this is what regulators are facing today. Okay. Let's go over briefly onto the energy policy, and then we will open for questions and comments. So the objective of the current energy policy is climate goals, which I think everybody of you know about. We are planning to have 100% carbon-free electricity by 2035, which is not far. And then there have been two major pieces of legislation that the recent administration has passed. One is the Bi-Partisan law. Has lots of components, but I've only explored the components that are relevant to the electric power sector. There is a fair amount of investment in transmission and electric vehicles, as you can see there. And then there is the Inflation Reduction Act. But we are a little bit short of time. So one key aspect I would like you to understand here is that the infrastructure law is grant funding, but the Inflation Reduction Act is a law that aims to generate money through tax reforms, and then those tax reforms are being circulated back into benefits for different climate and energy related funding. So BIL is grants and Inflation Reduction Act is incentives in the form of tax credits and loans. So you see a lot of that is tax credit for clean energy technologies, tax credit for electric vehicles, tax credit for new energy projects and loans. So on this slide, I would like to stop and open it for comments and perspectives. So from the knowledge of the industry structure and regulatory hurdles that we gained in the last 30 minutes, we can now have a better picture. We can now have a clearer understanding of, is the current energy policy effective enough to drive this change to net zero emissions by 2035? So here are some of the points for discussion. You could, if you are excited about the detail, the book has a lot of detail about that. But on this slide, I would open it for questions and comments. I mean, perspectives and comments. So go ahead.
Yeah, go ahead and ask questions if you may have.
I have one question. So there's this FEC, the FEC 2222 order, yeah, that was passed for the appropriate participation of the DERs in the electricity market. Like, how does that affect what you talked about people building, having residential solar and the GENCOs or the GENCOs, in general, not being able to get back their fixed cost and trying to increase the cost of electricity for the people without the DERs. So like, how does the FEC order, the FEC order 2222, like, how does it help in this case? Like, is there any correlation?
So what is FERC order 222? So FERC order 2222 is about the participation of aggregators in the organized electricity market. By participation, I mean that an aggregator can go to the market operator and say that I have this much electricity, I want to sell it in the auction, and the market operator is mandated by FERC 2222 to consider that aggregator as a generator and buy services from that aggregator if they are competitive. So according to your question, how does that help the generator to recover its fixed cost? I would say participation of aggregators is more of a market competitiveness enhancing measure. So if you let aggregators participate in the market, the idea is that since individual DER producers cannot meet the minimum requirements, like they cannot meet the capacity requirement, they cannot meet the cost of investment that is required, they do not have the technical skills necessary to, let's say, install an EV charger. So they go to the aggregator, and that aggregator provides the aggregation for kilowatt hours and technical service, and then that can enable a small DER producer to access the market operator's auction. So that is how it's not actually lowering the cost, it is just coming around a different way. So that might be a suitable answer for your question.
So a quick question about the arguments about letting utilities sell directly through EV chargers versus having other companies do it to promote competition. I'm trying to understand how competition in this case could ever be valuable or reduce costs for consumers, since it seems to me, say two companies in the same area are both going to be buying from the same utility, so they're going to be paying the same prices. And so the only competition is how much money are we going to skim off the top when we sell to consumers. So I'm trying to understand how that kind of competition helps at all.
So there is another dimension to it. You see, this picture shows you some of the empty corridors that have so far not been installed with electric chargers. So the point which is given here is that if you add a competitive competitor into that industry, this is going to accelerate the deployment of EV chargers. So you see utilities have, let's say, a specific fund, like they can install 200 chargers. Okay, fine. So why not install an additional 200 by way of letting other partners into the industry? So that is one benefit of competition. Another benefit is that the utility might be willing to establish them at specific locations only. But there will be some underserved areas, like, let's say, the highway between Pullman and Spokane, where there are not many customers. So who would be willing to sell that charging service there? So this is another argument in favor of competition. And then another argument is, I won't say argument, another point is utilities are like slow moving entities. They won't react very quickly to demand response strategies and other advancements, technological advancements that are going in the industry. So we expect that a private investor would be more responsive to demand response strategies and would be more responsive to ancillary services. So you can have those 3 points on the table, but that is still an argument, and there are pros and cons of both approaches.
Okay, thank you.
Let's take question from also people on the Zoom. So is there any question on the Zoom? People on the Zoom? No? So then maybe back, yeah, there is a question.
Great presentation, Ali. I just had one quick question that's more of a general question regarding adoption of the standards. So what, in your opinion, what gaps in the current energy policy can be improved to help push forward adoption of IEEE standards? And in my mind, I'm thinking of, we had 1547 at the distribution level for DERs, which is still slowly being adopted. But now with the inclusion of IEEE 2800 at the bulk level, as you mentioned, utilities are very slow and they only answer to authority having jurisdiction, right? So while these Q logs are backing up, these green policies are so aggressive, they're being forced to move at a faster rate, but they're not necessarily obliged to completely adopt on a global scale. So how could the current energy policy be improved, in your opinion, to help move global adoption?
So in connection with 2088, that is about, I think, interoperability between different distribution equipments.
IEEE 2800 is for like bulk interconnection of DERs, wind farm, solar farm.
Okay, but there are clauses about interoperability and.
Yeah, that is standard on interconnection and interoperability. Yeah.
So I would say that in this case, the incentives should go to, what's the correct word for that? They should go to key industry players, like what you call OEMs, like those that make the primary and secondary distribution equipment. I won't say the names, but I hope you get the picture. So these OEMs are responsible for making the technology equipment that other stakeholders in the market can buy, and that would help them comply the 1547 and 2088 standards. So that is how I foresee that. There are very specific clauses for promoting manufacturing of EV electric vehicles and chargers, but there are not many specific incentives for OEMs.
Okay, last question. Anybody has a last question? No? Okay, so then, and also anybody on the Is it Zoom or Team? So is it Zoom?
Teams.
Team?
It's in
Okay.
Teams.
Okay, so anybody on Teams has any comment, question? Okay, no. So then, once again, thank you, Mr. Ali Khan. I appreciate that. Was interesting presentation. We appreciate that. With that, thank you.
Everyone.